Okay, I don't know, something happened. Okay, now as I was saying, so essentially you can have something called as a computer program. You can replace this computer program with saying that it is a human being, and still this definition will hold true over there. Okay. Now the point is that this whole activity of learning, this has three different aspects over here. One is like you are learning to do a certain task, so that has to be preserved. So whatever is the task, you need to outline and maintain that task over there, and you need have the performance in performing that task measured using certain performance measure. And you also need to see that this performance measure keeps on increasing with respect to your experience. So as you keep on gaining on your experience, you should be seeing that your performance measure also improves over here, which is a very critical aspect. Now, that's the aspect about learning. Now, how this learning typically happens. Now, any kind of a data assisted decision making problem. So if you're looking into, say, a lab on chip kind of a scenario, what you do is, if it's for a diagnostic purpose, then you would be measuring certain attributes about chemical properties and other things over there. And as you keep on measuring these attributes, after measuring them, you have certain measurements, and based on the measurements, you are going to come up with a decision. So there is this kind of a relation which you will have to attach a particular measurement to a certain decision over there. Now, this kind of a attaching of a measured value to a certain decision can be done using very simple methods like a Bayes rule, which all of us had studied in very fundamental math classes. Now, what this Bayes rule typically says is something like this, that provided you know what is the probability of getting certain measurements for a certain class of a disease. So that is what we call as likelihood. So likelihood is a conditional probability that I know already what are the diseases which exist over there. So let me take the condition of leukemia. So whether it's acute myeloid leukemia or acute lymphoblastic leukemia, AML versus ALL, or it can be chronic myeloid leukemia versus chronic lymphoblastic leukemia, CML, CLL kind of a situation over there. So for the four classes, then my omega over here in the likelihood function is going to vary between 0, 1, 2, and 3 over there. So say I have four different variations of the classes. For each kind of a variation of a class, I will have what is my value of that measurement. So there are certain bioreactive molecules which I'm measuring over there. So what are the value of each of these molecules which is being measured? So if there are four molecules, then X over here is just a array which has four different measurements, which are four different values which are mentioned of the measurement over there. And the probability of encountering such kind of a measured value is what we call as likelihood. Next comes down the prior probability, and this prior probability is essentially the probability of encountering a certain class. And then comes down the fact which is called as evidence. So this is the probability of encountering a certain kind of a measured value over there. So given likelihood, prior probability, and evidence, these three together can be used to come up with a final decision in terms of a posterior probability. And this posterior probability is essentially the probability of getting a certain class, given that you know what is the aspect of, or what is a certain measurement. So if I have measured a certain concentration or density of a particular biomolecule, then what is the probability that I have either a ALL, AML, CML, or CLL, any of these four classes. So it is going to give me that probability over there, which is what we call posterior probability. Now, once you get that, then we take a final decision, and final decision is essentially my diagnosis, which is coming down over here, which says that what is the disease which is present given that I have these kind of measurements which we have observed. And that essentially comes down using this maximum a posteriori operator over here, or MAP. So what MAP does is it will try to find out what is the max probability which we get down, and then finds out what is the argument over their max probability. So for whichever argument you get the max probability, which is for whichever class the posterior probability is maximum, that is the one which is being attached to a certain decision. Now, from that, we would be able to come down with certain kind of a decision boundary, which is the one which is marked in this dashed red line over here. So what this decision boundary essentially says is something like this, that on one side of so it will basically cut this surface. So taken this example that there are two different attributes which are measured, and I took a very generic example, not suited to say lab on chip, not very specifically mentioned as lab on chip, but you can consider like X1 and X2 are two different molecules whose concentrations are indicated over here. So now that X1 and X2 are two different molecules whose concentration are indicated over here, now for one kind of a disease, you will have most of their attributes and decisions on one side, for the other on the other side. And there will be a very distinct boundary between them. So essentially what happens is, for this maximum posterior probability, if you go on one side of it, you will belong to one class. If you're on the other side of it, you are distinctly belonging to another class. This is what comes out as a attribute from this MAP. And that is what you see in the final decision making over here. So this separation margin is what is essentially called as a decision boundary. Now, how do we come to that is the primary question. Like, we need some data, and from the data we need to come to statistics, and from that statistics we will end up getting into probability, and from there we come into the decision making. But the primary point is like, I don't have access to raw statistics. I only have access to raw data. So how do we really come to statistics from data is the question over here. So the primary starting point for that is the Bayes rule, and it essentially starts from this thing which we call as a statistically informed decision. So the most common form in which we have seen generally Bayes rule being written is the one which is on the lower side of it, where the outcome or the output which we would like to obtain from Bayes rule is the posterior probability, which is essentially obtained by the product of the likelihood and the prior probability divided by the evidence. And in fact, evidence is a very critical fact. So evidence states that what is the probability that a certain feature or a certain molecule's concentration can be observed. And it's, as the name says, it's very critical over here, because this says whether or not X can exist or not. And if X can exist, so if the probability of X is 0, then that kind of an X will never exist. But if X exists, then the probability of that X is not going to be 0. It's going to be a non-zero number. Then we need to understand like what is that non-zero number which will come down over there, and that is my evidence over here. So now if we go from there and try to understand it, then we need to deep dive into get the points of like what we have at the end of the day is just a count. Okay, so from counting of certain objects, we will have to come down to its histogram, and from histogram, we will have to come down to the point of distribution. That's essentially what is critical over here. Now, how do we really come down to that? So let's look into this particular data. So what I have an example given to you where I have two different classes of objects. There are cows and there are cars. Now, and then say this is being measured by somebody who stood for 1 hour at any road in India. And the two most predominant things which you would see in roads in India are cows and cars. Human beings come secondary always. Cows and cars rule the Indian roads as of today. So over there, somebody is just standing and they are measuring out these two attributes. One is like what is the shade of color, whether it's completely dark or it's completely white. And if it's completely dark, then you mark it as 1. If it is completely white, then you mark it as 0. And any intermediate over here. So if you get cows which have different patches of black and white, then take an average of the intensity or the shade level over there, and that average value is what you put over there. Then you have the length of the car, which is another critical attribute which you need to look into over here. And this length of the car is or length of the cow, whatever. And typically you would see that most small Indian cars and cows are almost of the same length. They are sub 4 meters. So there's no great deal that most of them will be concentrated around the same place. But if you have a sedan or you're looking at an SUV, then they would be much longer cars over there. But cows don't come generally more than 4 meters. At least I haven't seen more than 4 meter long cows. So you have this measurement. Now what is the first thing? First we need to find out like what are the classes. There are two classes of objects which are cows and cars. This is critical. So you need to understand how many different categories in which the data exist. So if suddenly I ask you like what is the probability that this is of a dog, we don't have any evidence over there because the data did not, whatever data we were using for training our system, that never had any dog present in it. So I cannot really give you any idea about what is the probability of finding a dog if such kind of a measurement was done. So now that's a critical. So essentially what will happen is probability of getting a dog, which is that P of X is, that P of omega, which is the prior probability, will become 0. So you will never be able to solve it out. You will always say that for whatever be the features, I will never get a dog. Okay. Because in the training data, it was not present. So the first and foremost thing is we will start with the histogram, which is we count how many cows and how many cars are present. So omega 0 denotes the number of, omega 0 is the class of cows, omega 1 is the class of cars. So in this picture, we can count and see that there are 7 cows and there are 4 cars present over there. Great. Now from here, I will be able to find out the prior probability, which is what is the probability of randomly getting a cow or randomly getting stumbling upon a car. So the probability of getting a cow can be 7 by 11. Probability of getting a car is 4 by 11. This is one part which is done. Next thing is we have to estimate what is the evidence and then go on to estimate even the likelihood. So for that, what we do is probability of stumbling upon an exact feature is practically 0. I mean, that's from a probability theory itself. So you will never land up on an exact value over there. You will land up, you can always find out a probability for a range of values. So what is the probability that X varies between a minimum limit to a maximum limit? So what is the probability that the length of an object is between 1 meter and 2 meter or between 2 meter and 3 meter? But you cannot say what is the probability that the length of the object is exactly 1 meter. That is essentially 0 from a theoretical standpoint. You will never have something which is exactly 1 meter. There will be some deviation over here and there, plus minus. There is some error which will always creep in over there. So now what we see over here is that we want to count the number of objects, and for counting them, we'll have to count like what is the number of features which are present over there. So what we do is we basically divide them. We slice out this feature of x1 and x2 into different blocks. Okay, and then count. So each of x is essentially my count of finding out a certain object with a certain value of feature over here. You would see that in certain blocks, I don't get any observation. So in this block, or this block, or this block, I don't get any observation over there. So essentially, there my evidence is going to be 0, whereas in all the other blocks, whereas in this block, I see that there are 3 cows. So the evidence over here is essentially equal to 3. But then this is not probability in any ways. So how I can obtain that thing called as evidence is I divide the count over there by the total number of counts, or essentially the total number of objects which I have over here. So that gives me 1 by 11 times of this matrix, and which is a good way of finding out how many, like at which feature I have something. So this gives me my evidence over here. Now similarly, in the same way, I can get my likelihood as well. So first I get my likelihood for my class of cows, which is omega 0. So this is what my matrix will look like. Then I get my evidence for my class of cars, which is omega 1, and this is what my matrix looks like. It's you would also interestingly find out that this evidence over here is essentially a summation of the numerator, which is the product of the likelihood and the prior probability taken over all the classes. That itself is going to give you this measure of this probability, which is called as evidence. Now let's look into this particular point, which has a cross mark. So if I want to find out that if I'm given that measurement of x1, x2 over there, then what is going to be my probability of getting a car versus what is my probability of getting a cow. So my probability of getting a cow, as it turns out over there, is basically 0, and that is 0 because the likelihood over there was 0. Similarly, the probability of getting a car is equal to 1. That is what I end up getting over here. And essentially there was a car in my training data set. So whatever observations I had collected, I did see that there was a car present over there. So this is correct. I'm not wrong in any way. I'm correct completely over here. Great. Now let me find out another point over here. So this is another point which is marked in cross. And then I am asking you, like, what is the probability of getting a cow or a car over here? Now, interestingly, look over here that the likelihood for the class of cows or for the class of cars is essentially 0. Now, because my likelihood is 0 over here, then how do I get my posterior probability? That is the question. So my likelihood is 0. Then the question is, how do I get my posterior what do I get over there? So I don't know, because my likelihood was 0 and my evidence is also 0. There was nothing which was observed over there. So now, since my likelihood and evidence, both of them are 0, so I get into a 0 divided by 0 problem. So how do I find it out is the question. So what do you think? What can we do? Anybody has any thoughts about it? Would anybody like to specify something? Any thought? Like if I encounter this kind of a situation with a 0 divided by 0, then how can I still go around with making a decision? Or should I stop over here and not make any decision? Any thoughts which you would like to say on how we can make a decision over here in case we encounter a 0 divided by 0 problem? Anybody would like to have any comments on this, or is it like it's really going off your
Sir,
mind?
when evidence itself is, sir, when likelihood is 0, or then what is the meaning in proceeding further, sir?
So that's the point. I mean, in your experimental data, when you had collected the data, you did not have any such value of observation, but suddenly you got this value of observation when you were deploying this. So it's like you created a lab on chip for a certain kind of a blood test, and you had a decision which was made based on whatever observations you had found out in your training data. But now you don't have any decision. So now, I mean, you encountered certain kind of a value of those chemicals, those bioreactive molecules over there, but you had never seen them when you were testing and calibrating this device. So then what do you do? What will you say now?
Yeah. Generally, in normal other conditions, whenever we get 0 by 0, L hospital's rule we used to apply now, sir, in normal mathematics.
What can you do? I did not understand.
In normal expressions, whenever we get a 0 by 0, we use the L hospital rule, that is differentiate. Okay, that may not be
use L'Hopital's theorem, but the point is that in order to use that, it needs to be that's like a differentiation thing which I'm saying. So when you are under limiting condition, if you get it down and you have a polynomial expression. But the point is here it's not a polynomial expression.
Polynomial expression. No idea, sir.
So this is where I will bring in this concept of distribution. So see, what you had observed over here was some discrete time points and discrete stamps of the data. It does not necessarily mean that this is the distribution in any way. So what you are observing is okay. I mean, that data was present in that particular way over there, and there wasn't anything which was specific to whether this was really originating in a particular way as it should have originated over there. So this is going to create a bigger problem. So because you never knew anything about the method of origin of the data. So we need to understand about this concept of distribution. So what distribution essentially says is that if a random value is occurring, then a random value has a certain probability with which it can occur, and there is a process which keeps on generating these random values to occur. Now I would be referring back and forth and saying that these are random values, but essentially the way they occur is it's through a process. And what we are doing is that I haven't seen a process for infinity. And that's why I don't know what is happening throughout the life of this process. I would have seen this process for a certain fixed period of time only. I don't know what is happening throughout its life. Now that I don't know what has happened to this process throughout its life, and I'm just seeing it only for a fixed period. So what is there in this fixed period is what I have measured. Now the point is, from this measurement of a fixed period of type of a fixed period, can I come to a point where I can estimate like any other thing which can get generated from there, and that kind of an estimation can be done using a distribution model. So in general, let us assume that these two variables x1 and x2, they were getting generated from a multivariate normal distribution process over here. So multivariate normal distribution can be represented using a polynomial value, which is an equation which is represented like this. Now, what we have in this multivariate normal distribution process is if I mark this particular location of x1 and x2, then what I need to do is I had a certain set of measurements. So from there I can find out what was the mean of x1 and x2 for the class of cows. Similarly, I can find it for the class of cars. Now I can also find out capital sigma, which is the covariance matrix over there, the covariance of x1 and x2 for the class of cows and separately for the class of cars. Now from there I can evaluate phi for a particular class, so either for cows or for cars, and then from phi I can get down my likelihood, which is p, and from likelihood I can calculate my evidence. Now even if I had never encountered that data during my training process when I had this observation within a limited experiment which I was recording, even if I did not have that particular data available to me, still I will be able to, under a certain degree of uncertainty, very likely predict out what was this particular value over there. So that may not be an exact distinct value, but it would be some sort of a representative value. And there is also an uncertainty which is always associated. Now, if we put this kind of put all of this known data and estimate what is mu and sigma for each of the classes, and then we put our value of x at that particular point, I might end up getting that the likelihood of my class of cows is 6 by 14, and the likelihood of getting my class of cars is 1 by 14. Now, as a result of this one, I would end up getting that my likelihood of not likelihood, my posterior probability of getting cows, which is P of omega given X, is 42 by 46, whereas P of omega 1, which is probability of getting a car, given that X is 4 by 46, and from there I can come to a decision that most likely over there I might encounter a cow rather than a car. Okay, this will be one of the ways in which we really solve it out, and these kind of measures of estimates really help us in solving problems where we don't have enough of data available from evidence during the initial experimental stage itself. Okay, now this is a small quiz in order to just do a de-tiring of this continuous process. So does anybody know this person? So just a small trivia from the history of IIT. Would anybody be able to tell who is this person?
Anil Kumar Gan.
Great. And like, if I ask you, how did you find that out?
I had seen this in one of lectures.
You had been to any of my previous lectures?
Yeah.
Okay. Did you know the answer? I was expecting somebody would come up with a much more innovative way and say, like, I did a Google image search and found him out. So anyways, he is Anil Kumar Gain. So actually, he was a former professor of the mathematics department at IIT Kharagpur. He was a very like illustrious professor over here. And in fact, like a big credit of his is that he was the UGC working group chairman. Sorry, he was the working group chairman for NCERT. So whatever you see in the primary school level curriculum is something which came up during the era when he was the chairperson of that one, and then he was the working group chair as well, which came up with like what should you teach in a unified school curriculum to kids so that they are of real useful when they grow up. So now just a trivia. The reason why I came back is like a lot of the statistical decision making and everything which we do today is based out on this Pearson product moment correlation, and that's something which was done by Guyan and Ronald Fisher. You might be hearing a lot about Fisher's linear discriminant analysis and all of those things, but very few people really go to the trivia and understand the fact that it was not just Fisher, but it was Guyan and Fisher together who were working on that one. So anytime you just use a Pearson correlation coefficient or something, which we trivially do for really putting out to experimental facts in journals that our data from experiments is good, then we need to realize that it's not just only Fisher who came to that one. Only Fisher wouldn't have ever come to that, but you also have Guyan. So a small trivia just to say that things were very important within our country itself. Okay, great. Now from that trivia part comes down the next issue, which is concerning uncertainty in decisions. And this is something which really keeps us worried. Now, as I said, you will never be able to measure an exact value. You will be able to measure a value within a certain range. That's it. Now, because I'm not able to measure an exact value, but I will at most be able to measure a value within a certain range. So that is going to be very critical for me. Okay. So now let's look into this one. So one is like, this was very famously developed by this person called as Claude Shannon, famous mathematician, and then eventually it led to the birth of something which is called as coding theory, based on information theory, and coding theory was done by Thomas Cover in a big way. But then let's look into what this Shannon really said out. So he said that guaranteed events have really no information, which is the sun rises in the east and sets in the west. It's a guaranteed event, so there won't be any information. Less likely events should have low information. Sorry, likely events, very likely events should have low information, which is like it's cold in the winter. I mean, okay, it's cold. I mean, today morning it was 20 degrees centigrade at Kharagpur, which is okay. I mean, it's November. It's the first week of November, and then we are pretty much in a place which gets cold. So 20 degrees centigrade in a November morning is not that big deal. So there is very less amount of information. If somebody would have come and said like it is minus 20 degrees centigrade in the November morning in Kharagpur, then like it's a very less likely event, and then the information is very high. Similarly, like if somebody says that the sun rises on the west, great. I mean, it's the least of the likely events which can ever occur. So the information content over there is very high. Next, which we have is that independent event should have additive information. And so the certain information about the rising of a sun and certain information about some other independent event is like a star shooting into Mars. They are two different things. So they will have additive information over there, or something like say you catching flu and your best friend getting diagnosed with diabetes. They are two very independent events itself. So there is no circumstance. If both of you caught flu, there is still a dependent event that maybe you were together at some point of time and you got flu. I'm not speaking about COVID in any chance again to get everybody more worried about it. I'm going to use this example of flu, but otherwise it's not so. So that's the point over there. Then it comes down another aspect, which is like we look into information or self-information. So for a given event or a measurement X, the self-information which it contains is just log of probability of that event to occur. So if X is a measurement which we had found out, then P of X is essentially that evidence which we had. So information that we encounter certain experimental observation is that log of P of X. So in case we would never encounter a certain kind of an observation, so P of X is going to be 0. So log of P of X is going to be infinity, and that will be minus infinity, and it will be infinity, and then this information is going to be minus infinity. Whereas for all other particular cases, it will be a fractional value. That's why that log of that fractional value is going to be a negative number. So you offset it by putting down another negative so that information is positive. You are not stumbling upon negative information. Next comes down that if this information is represented not in log of exponent or natural logarithm, then it's called as bits in case it has a base 2. Similarly, there is another concept which is called as entropy. So entropy is essentially the summation of information of all possible events which can occur over there. So that's because it's a summation or it's some sort of an averaging over there. So we use the expectation operator. So expectation operator gives us that if a certain X has a probability of P of X, the information is log of P of X. So then this expectation over it is basically a summation over all possible X of P of X log of P of X. And P of X is a probability which is dimensionless. It does not have any unit. Log of P of X is in unit of information, which is nats, if it's to the base of natural logarithm. So then you just have Shannon's entropy expressed in nats, as in over here. Now comes the relationship between information and entropy. So let us take this particular example over here. So if I'm looking at the case of only cows and cars, I'm not looking at a particular value of X over here, but my X or this independent parameter over here is just whether it's a cow or a car. Then I can write down my probability of getting a cow as 7/11 and that of a car as 4/11. Now from here I can derive what is the information of getting a cow and what is the information of getting a car. And from there I can come down to the point of entropy. So now that I come down to this point of getting an entropy, so this is what my entropy will look like as I see over here. Now comes the point that if that's by nature of seeing entropy, so let's look into information itself, and that is with respect to this particular measurement X. So at this particular location which I'm pointing out where X was equal to 0, so my information over there is something as a value which tends to infinity. Similarly, if at any other point where it was 3/11, I had a valid value of it. But then if I find out my entropy over there, how it will sum up is something like this. For all places where I had not observed any experimental data, so my X was essentially not present. So essentially it turns out that P of X is equal to 0 at those points. Because P of X is 0, so 0 multiplied by log of 0. Log of 0 is a value which tends towards infinity but is not exactly infinity. So a very high value multiplied by exactly 0 is again what gives you 0. That's why despite information reaching to infinity, your entropy will never reach to infinity, and entropy is always a bounded fixed number. So there is a lower bound and there is an upper bound. The lower bound of entropy is always 0 because it's only one particular class of object which is present. So P of X for only one value is 1. So then you have P of X which is 1 and log of P of X log of 1 is 0. So 1 multiplied by 0 is what is 0. For the highest value of entropy, what you would get down is if there are n number of classes or n number of particular ways in which this variable can be arranged. So if every of them is equiprobable, then you would end up getting the situation where I mean it's essentially the maximum entropy over there. Okay. So now let's look into this in the similar way, like what is the entropy for my number of cows, and this is what it turns out for my cars, and this is what it turns out over here. So now the point is, like, what do I gain by looking into these ones is very critical. So generally, I would try to have a data where my entropy is somewhat towards the maximum value of entropy which can be attained over there. So any value of entropy experimentally observed which is lesser than the maximum value of entropy which I can attain is something which I am not going to prefer to have over here. So this is like really a crux point which I need to observe over there. So from that aspect and attribute, what we need to understand over here is that entropy cannot be to the entropy cannot be towards zero. Entropy needs to be a very high value, and since we know from a theoretical standpoint what can be the maximum value of entropy, so we'll always try to push entropy to go up to that particular level over there. So are we good with that? Nobody says anything. I think most people are not getting it. So now here I will come down to the point of, as I said, that it's about a mathematical understanding of deep neural networks and why we go into that aspect. So the first part is like deep learning as such, whatever you see the buzz or the hype today is not something which has happened because of just today. It has been there, it has been growing for a real amount of time, and somewhere around 1940s is when it all started with it being called as neocognition, or a new theory of cognition or cognitive reasoning is what it started with. And then eventually it moves over to deep belief nets and comes on to representation learning, and then eventually what we see today in terms of what is called as deep learning. Now let's look into a quick recall over here. So what we said is that we are going to take a decision using something which is called as a Bayes rule, and as a result of Bayes rule we will be able to take the final decision using maximum posterior probability, which itself is going to give me this kind of a decision boundary, or what we call as a margin. Now the shape of this margin is something which is very critical. This has a very important say landmark behavior of how it works out over here. Now let's look into the challenges with the decision boundary. So one is, if you have abundant number of samples over here. So if I have abundant number of samples, it's really good. I can actually have a decision boundary is very distinctly definable over here. Great. In case I don't have so many abundant number of samples, then this definitely can be one of the decision boundaries, but we also need to really respect that this may also be another decision boundary, which actually satisfies all the conditions of it being a decision boundary, because on one side of this particular line is one class, on the other side there is another class. So there is no way that it violates any principles from being served as a from serving itself as a decision boundary. And then you have another scenario which is called as the scenario with the scarce samples case. So the samples are so less that here this may be a decision boundary, this may be another, this may be another. So there can be numerous possibilities of ways in which decision boundaries can be created over there. So that's the situation around with a scarce sample. Now, in order to understand this challenge, let us deep dive into it. So what happens is, all of these nature, like whatever is the nature, whether it's of a polynomial curve or whether it's a straight line, is something which lies in understanding the likelihood over here. So if this likelihood is a cubic polynomial, then your decision boundary will itself be a cubic polynomial. If this likelihood is something which can be defined using a quadratic polynomial, then your decision boundary will be a quadratic polynomial. If your likelihood itself is a straight line equation, it's a linear or first order polynomial, then your decision boundary itself will also be a first order polynomial over here. So this is one of the problems which we really need to understand on creating the model. And one point which we need to appreciate over here is that the more and more complex your model tends to become, the harder it is to create that model. Because say I have a linear equation over here, which can be written as x2 is equal to m times x1 plus c. Okay, m and c are the two free variables using which you set down certain values of m and c, and then you will be able to define a straight line which is going to serve as a decision boundary. Great. The moment I define that as a quadratic, then what will happen is it will give me a form like ax1 square plus bx2 square plus cx1 x2 plus dx plus dx1 plus ex2 plus f is equal to 0. Now it means that I have to have these 6 free parameters a, b, c, d, e, f. The 6 free parameters which need to be tuned in order to come up with a generalized equation of a quadratic over there. So there is a degree of change or a degree of complexity change which we observe over here. If it's a linear one, then I just have 2 free parameters to tune over here. If I see it as a quadratic one, then I have 6 free parameters to tune, and that itself is a very challenging task. Now from there, if we go to the point that, okay, I will just stick to a linear equation over here because I just have 2 free parameters to tune over here. But then in case you don't get dense or abundant samples and you are left with just scarce samples, you would see that there can be many possibilities in which this can occur over here. So as a result, you know that there can be many possible values of m and c which can be tuned, and that's going to create the problem. So you don't have only a unique combination to occur, but there can be multitude of those combinations which can occur over here. So this from this particular point, when I have tried to explain you at least like where all of these problems are, we can look into like how we have traversed this whole age. Like we have come down from the age of very standard rule-based AI onto this age of what we know today as deep learning. Now, how it has progressed is standard rule-based AI is like a switching rule. So it is very similar to what we still have in our air conditioning system. So if you set your temperature for air conditioner, say at 25 degrees centigrade, then it will continue to work at 25 degrees centigrade. And how it does is very simple. So for a standard, say an old generation or the classical compressor based air conditioning system, it will switch on the compressor till the temperature goes to 25 minus 2 degrees centigrade, which is 23 degrees centigrade. The moment it hits 23, the compressor stops, and it's in a stopped condition. So there is no heat pumping going on. So your indoor air is heating up, and the temperature is increasing inside over there. And eventually you see that the temperature increases and then goes up to something like 27 degrees centigrade. The moment it goes to 27 degrees centigrade, then the compressor again kicks into action. So it starts pumping out heat. So you would see that you are never exactly at 25 degrees centigrade, but you are fluctuating in a plus minus 2 degrees way. And it does not take into consideration any other effect over there. So that's about the standard rule-based AI. Average behavior is great, but point-to-point behavior is not so good. And I mean, from a comfort point, nobody likes those binary switching ACs in any way. Either it's too cold or it's too hot. It's never optimally at 25. Now, from there comes down this classical ML. These are what are called as those weather controlled or climate controlled ACs. A lot of cars today come up with that one, which is they would vary the speed of operation of the compressor, as in an inverter compressor kind of a thing.
તમારો અહીંયા કીધેલા છે કે કરવાના એમ મને પણ એ તો નહીં આવે ને રિસર્ચ સેન્ટરમાં નહીં કર.
Okay, there was too much of interference, so I muted somebody who was unmuted. Okay, so now the point is that in this kind of climate controlled ACs and the behavior over here, you would see that they use some sort of a machine learning behavior. Generally, these are fuzzy logic controllers, but today people are even going down to learnable mechanisms of maintaining climate control over there. So how this works out is pretty straightforward. So you would see that it doesn't take only temperature as an input, but it would take a certain number of other conditions as well. So what are other environmental conditions? Now, based on all the environmental conditions and temperature which it takes in as input over there, It's going to learn from your behavior, like your pattern of switching on or switching off an AC. It will try to gauge like what you would prefer to have, and then come up with a decision in terms of this control variable. From there, we come on to this age of what is known as representation learning, and a very classic example is image compression, as in JPEG image compression, or even video compression with H.264 or HEVC, where a lot of learning is involved in order to see that there is some sort of a way in which whatever features are to be stored, they are also optimized. So you just don't take in any feature and work it out over there. And then comes down to the point of what we know as deep learning, or deep learning of the age, which is as of today. So not just looking into learning of features, but we come down from deeper features to lighter features. And one of the reasons for that is essentially to come down to easier solvable polynomials. So you did see that you can have a higher order polynomial, but any higher order polynomial can be represented. So a quadratic polynomial can be represented as product of two linear polynomials. A third order polynomial or a cubic polynomial can be represented as product of a quadratic and a linear, or again the quadratic can be broken down into two linear. So it's basically product of three linear polynomials. Now, when I break it down and do it in a subsequent stage by stage, so we would see that it's much more easier to solve them in some way. And that's something which is of great importance over here. And that's the way how deep learning is really progressing. Like what we really want to achieve in machine learning is something like this, that there are three primary attributes which we would like to preserve. Okay. Now the three primary attributes which we would like to preserve is something like this, that first part of understanding over here is to understand what is the data plane of this problem. So what is the nature of the data? So if we have a lot of data which is dense and abundant, then it's an easier problem to solve. If we have lesser amount of data or not so abundant data, then it's a harder problem to solve over there. And that's how the order of complexity increases. So it keeps on increasing towards the point where we have less amount of data from the point where we have more amount of data. The next part or next aspect which we need to look into is what is called as the model selection plane. So this is something which understands like how is the complexity of the model increasing. So as we start from linear, where we have a very simple model to work it out, and keep on going towards cubic, where it's a much more complicated model to work out. So the complexity of the model keeps on increasing. Then we have another attribute which is called as the control selection plane. So what happens in the control plane is that we start from simpler ways, which is say optimizing or essentially fitting or like tuning the free parameters in the model so that the model starts replicating much closer to the data over here. So essentially we fit the parameters of the model so that it best represents the data which we have over here for our training purposes. So the easiest one is to work out on the maximum likelihood estimation, or MLE. Toughest is as we keep on going towards something which is called as perception loss. So let's get into deep dive and understand each of them one by one. So the first part, which is to deal with the space or the data space of the problem. So what we need to do is something like this, that we might not always have dense samples. So which is ideally I would like to have this kind of a scenario where I have a lot of samples, but in all practical purposes, I will get on this kind of a scenario where I don't get so many samples. Now, can we do some operations on this kind of a data where we don't have so many samples and arrive to a point where the modified topology of the space looks that it has a lot of samples over here? So one of the ways of doing it is by way of something which is called as augmentation. So either you can rotate or you can flip, and you can flip them in flip up down manner or flip left right manner, any of these manners in which you would like to flip them. And you can create more amount of data. So typically, like say these are WBC images. So the pathological nature of the WBC has never changed. The only thing which has changed over here is the appearance which it is coming. So the disease state, if it is healthy, it is still healthy. Even if I rotate the image of a cell can rotate itself. So even a rotated version of a cell's image is still the same cell over there, and there is no change which happens to it. Now, what what becomes interesting is that as I rotate these particular cells over here, so we would see that while appearance changes, their pathological nature remains intact. It does not change, and as a result of which, I would see that I can still sort of like retain their nature. Now, the issue is that don't try to do the same kind of operations on any kind of an image. So if I have, say, instead of a cell, I took the image of a cow, and because I had a flip up down, which was a valid operation, I did that on a cow. Now a cow will get flipped, but then in reality, this kind of a sample will never occur. That's the bigger problem. So don't end up creating such kind of say transformations which are very unrealistic in nature. The moment you create transformations which are unrealistic in nature, it really doesn't serve any of our purpose over there. So that's something which we need to really learn how to avoid. And that's the reason why the whole thing of data augmentation is something which is called as art of data augmentation rather than science, because it's not a direct rule base which you follow. There is a lot of domain level understanding which needs to be given, like you need to take them into consideration itself. The next part of the problem is something where we need to understand about the model selection plane. So what we do is typically, say I take that example of a representation learning based mechanism, where say that this decision boundary which is getting created over there is something like a quadratic. Now what I do know is that if I want to solve this problem easier, I would rather prefer to have a decision boundary which is linear and not quadratic in nature. So what that means is that if I can have another layer or another abstraction of working over here, such that the sample points over here are converted and arranged in such a way that they do not become quadratic and they become linear in nature, then I should be able to solve it out. So how can we do it? So one of the ways is that I insert a particular layer which takes in this abstract representations and converts them to a particular form, such that this new form is more of like what can be linearly separable by a straight line. Now the question which I will ask you is that what kind of an operation do you think is being done by this abstract, by this layer which is learning abstract features, such that it can convert a quadratically separable feature space into a linearly separable feature space? What do you think? What kind of a transformation operation can convert this one? Any idea? Any thoughts, any idea of how we can convert a quadratically separable feature space representation to a linearly separable representation? What can be a transformation which can be done on these features? Nobody has any idea? You just need to convert this representation of the learned features x1 and x2 from a polar domain to, so imagine this to be a Cartesian domain representation. You need to convert it to a polar domain representation with a centroid taken in the middle of this one. You would see that because these red circles over here, they are much closer to the centroid, so they will be having a lesser distance over here, and these ones will get separated. So essentially what's learned over here is a separation which we just convert something from a Cartesian to a polar representation and nothing beyond it. Now comes the next part, which is about the control plane of a problem. So the control plane is essentially something which looks into how do you fit, how do you tune the parameters of the model such that it fits to best represent the training data which is provided to you. So one of the ways is to create something which is called as a maximum likelihood estimation, and then go all the way up to something which has to do with something which we call as perception loss, which we do. So something about perception loss is, say I want to train a model which takes in images or hand-drawn sketches, and I want this model to be able to predict out something which looks like a photograph. Now, if it predicts something like this, it's never closer to a photograph. There is some transformation which is done on the hand-drawn sketch, but definitely it's not a camera photograph. So on the other side, if I have an image like this, which is created out of this particular model, which looks more closer to a camera photograph. Now, what you can say is that if I'm measuring mean square error, which is point-to-point errors between the hand-drawn sketch and whatever output I'm looking at, so the point-to-point error would be very high in case of the second one, which is a photograph. So there is a very high mean square error. But again, the second one is something which looks like a photograph. So your perception loss is much low. Whereas on the other side of it, I would see that the mean square error, point-to-point correspondences are much lower, but the perception loss that is it a photograph? No, it's not a photograph. It does not look anywhere closer to a photograph. So the perception loss is very high over there. So this is something which is an interesting fact which you will find out over here. The challenge obviously is that how do you learn perception losses? Now these are because they are not designed, so you don't have a hard definition of what is a perception loss. So you will have to learn it up completely. So there are different ways of doing it, and one of the ways in which we do it is using something called as a neural as a discriminator function, which is again implemented with a neural network. It's a very simple neural network whose job is to learn to discriminate between an actual photograph and a generated photograph over there. So the better and better this sketch to photo CNN becomes in generating images which look like a real photograph, this discriminator's error will keep on rising over there, because it will get confused like what is a photograph and a real photograph versus which one is actually generated over there. And the more and more it happens, you know that whatever you have generated is the best one over here. Nonetheless, almost coming to an end. If you look into this complete ecosystem of how these things behave, then deep learning is sort of like a subset within representation learning, which itself is a subset in machine learning, and that itself is a subset within AI as we go forward in looking at it today. And from starting perspectives, these are a couple of books which I generally recommend. So if you are somebody who is beginning and you generally don't have a very good grasp over linear algebra, then you should be starting to like interpret this slide from right to left on the reverse order. So if you're not good with linear algebra, you don't think that you have a formative basic, then please start with Gilbertstrand's book on linear algebra and learning from data, and then move over to neural networks and learning machines by Simon Hakin, and then move over to the book on deep learning by Ian Goodfellow. And that's typically the order in which I would recommend that you do it. These are a list of a couple of journals and conferences where most of our community publishes, and if you would like to get deeper understanding, you can. So there is nothing on lab on chip which gets published over here, but in general, if you want to understand machine learning and data sciences and data analytics as it goes out today, then these are the places where you would see the top-notch problems of the day getting solved. So, and finally, just a small shout out about this new initiative which we have at IIT Kharagpur. So if you're looking at interesting positions of, say, applied industrial research within an academic setting, then just visit our website on AI for ICPS to learn more about what we have to offer today on that, including a lot of career options as well. So that's all what I had to say for this one, and we still have a couple of minutes left, so I can use this time to answer any of your questions related to the talk or about data analytics and apply to your lab on chip solutions in general as well. So anybody has any questions, then I am open to answer them as well. Okay, so if we don't have anything, then let us close for the time, and I will just request the coordinator and sir, book names one more time. Okay, these are the names of the book on the slide over here. Okay, thank you all then.